It's all about Intel today.
Okay.
Intel. Come on.
Okay, we have to start somewhere. So we should start just with Intel. Because I have to start somewhere,
Yeah. Well, every
Anyways.
bad story needs to have a start.
Anyways, I don't think that the bad story is the bad story is a bad story. Anyways, I think that the thing that started it all wasn't Intel at all. It was the, how were they called? Fairchild.
Okay.
And the money that NASA basically threw at Fairchild to enable them to create chips.
Well, we'll have a story. We'll have a chat about that actually. But before we start doing that, welcome to ThatITShow podcast. To the latest episode. Let's roll in the intro and let's start chatting. I have an intro question.
Okay.
Because I think that the part of our conversation today is probably going to involve some of the keywords and topics that I want to ask questions about. Now you have become the Mr. Computer Architecture in the past couple of years for us.
Yes.
At the university, I stopped doing most of the lectures for a variety of business reasons, which means that I get to bug you and nag you and just throw questions at you as if I don't know anything about it, which is a very comfortable position for me. So my intro question is bitness. 4-bit versus 8-bit versus 16-bit versus 32-bit versus 64-bit. What the hell is that all about? Explain to our audience as best you can.
Depending on what you're looking at, some people tend to think that bitness, or the number of bits, is something that is fixed. So 64 bits means that everything inside your computer is 64-bit. But in reality, it's the largest size of register that you can actually work with. So basically,
it doesn't have to be that way, but you're mostly correct.
I'm trying to make it sound less complicated than it is. Basically, if you want to calculate anything, the largest whole value that you can work with, or the
integer value,
the integer value that you can work with, is going to be dictated by bitness. Mm-hmm. So depending on the processor, depending on the size of the registers, the way the registers are working and so on, it means that for a 6-bit processor, you are going to be able to work with 60-bit of data at a time. I'm not going to say in a single cycle because this is not going to be true. But
depends on the data type.
It depends on the data type, depends on the. But the idea is that you are able to work on data in chunks that are going to be
increasingly larger the greater the bitness is.
Basically equal to bitness. So an 8-bit processor is going to be able to work with 8-bit of data at a time, 16-bit of data, and so on. But sometimes people interchange this with the address bitness, because a lot of the processors have the same bitness when it comes to the size of the registers and the amount of memory that they can address. And in this case, bitness of the memory basically means how much memory they are able to address directly without doing any page swapping and so on and so on. The reason why this is sometimes the same and sometimes different is that the older processors, especially the 8-bit ones, had a big problem. It doesn't make any sense to be able to address only 256 bytes of RAM. So they had to have either 16-bit or other values of bitness. From the top of my head, I don't remember any other combination.
There are the opposite combinations, actually.
Yes, but I don't remember any other combination of the bitness when it comes to addressing space. Or to be more precise, I'm not able to remember if there are any other processors that were 8 bits inside and at the same time able to address between 8 or to 16 bits, so 12 bits and so on. On the other hand, the first processor that we are going to be dealing with today, 4004 Intels, had a 12-bit addressing space. So they did something that was different. And the reason why you would like to do this, or you would want to do this, is because you want to save on circuits inside your CPU.
Yeah, die space is very important when talking about this.
And this is one of those things that saves die space, because if you are grabbing information from the memory, that is going to be 16-bit locations, you need that many logic gates, and in order to be able to address the memory, increase the counters and so on. So this just adds additional elements to the die. And since we are talking about, let's start talking about the actual processors, because I have it in front of me. I just want to say that we are dealing with a processor that was doing everything that it did in 2,300 transistors.
Yeah.
So this was the I would say hard limit that they had. But before we do that, let me just interject with a small thing, because I want to put things into perspective. I want to talk about a guy named Noyce,
Okay.
who was actually one of the founders of Intel.
Correct.
Because in the 50s, he was known as one of the treacherous 8. Because what he did is he went from Shockley Semiconductor, and then
Shockley was one of the people related to the invention of transistors.
Yes, and then he created something called Fairchild. Okay, Fairchild, first it was called Fairchild Common Instrument, and then Fairchild Semiconductor. And the reason why this is important is that they were the one who did the most experimentation on MOSFETs. And this is the thing that enabled a lot of designs for something that was first analog circuitry, so more or less amplifiers. And then they switched over to creating the integrated circuits that were also operation amplifiers, but they were integrated, so no discrete logic there. And then they created first resistor, transistor logic circuits. And the thing was that what they did is they created the logic interfaces and the logic circuits that were used in the Apollo guidance computer. And why I'm going to try to wrap this thing up and say why this was important, because at a given point in time, NASA had to help Fairchild to create integrated circuits that made sense for the actual Apollo program. And they had to heavily invest into Fairchild because they weren't able to meet the standards that NASA needed. And I read somewhere that in one particular year, I don't remember which one was that, something in the
60s.
early 60s, NASA was buying something like 98% of all the output that Fairchild was able to put on the market. And they were the only ones creating integrated circuits. And the reason why they did this was not only to enable them to have all the circuits they had, but in order to make Fairchild a competitor that is able to actually create something. So they had a relationship where NASA was just bleeding money into Fairchild to enable them to create chips.
Okay.
And this is one of the cornerstone moments when it comes to chip technology, because if they weren't for Apollo, if they weren't for NASA that spending all that money, I don't think that Intel would even exist.
I agree. Actually, two more points to that. One of them is expansion of something that you said, and the next one is actually a potential question that we can also discuss a little bit. To expand on the topic of bitness versus the circuitry size, which is super important discussion. Hence the reason why we currently don't have stuff like 128-bit processors, natively at least. Because with the technology that we have today, the chip size would be so enormous, it would bleed so much power, it would require so much cooling to do all of that, it's absolutely not viable. That's the first thing. The second thing, you can actually think about this in completely opposite way to how usual engineering works. If you talk about 128-bit computing, which is, what is the exact problem that we would try to solve with 128-bit computers? The answer is there is no problem that we should solve with that, because with current hardware we can solve all that we want at this point in time, which means you would basically, if you are forcing to industry to do 128-bit CPUs, you would be in a situation which we usually call solution with, solution that just doesn't cover any kind of problem. Solution for a non-existent problem. So that's my first point. Not necessarily for some political or human reasons that are based on weird stories, but for the perspective of what comes after that, which is the Moore's law and whatnot, because the relationship between bitness and Moore's law definitely exists. Second thing, just give me a second more. Coming back to the topic which you touched upon, which was that basically what you said without saying it out loud like that, is that the implementation of the CPU is just as important as the bit width of the data path or the registers or whatever. And this is still true today, because 64-bit CPUs of today, they do not have 64-bit address space. They have 48-bit address space. So it's vastly different. And the reason for that is exactly the same. There is no need for it. Or if you want to put it into engineering perspectives, again, you would have to enlarge some things on the CPU so much that it wouldn't be viable, and the price of that and all of the other economic aspects wouldn't work.
I would just go with the simple engineering thing with nice to have and must haves.
Exactly the point.
What you are dealing with, and I just had the...
And of course, OS support.
But okay, OS support will come. But the thing is that I was just talking to students today when it comes to computer architecture, and I was trying to paint a picture of what is currently bothering people who are trying to design chips.
Okay.
And the thing is that you can create a chip that is going to dissipate, I don't know, on a normal chip die, and I mean normal, something that we are used to. So something is going to be probably as big as the biggest today's chips. Mm-hmm. You can try to dissipate up to probably 1 kilowatt. Mm-hmm. But what you cannot do is you cannot create a cooling solution that is going to be applicable to normal users. Yeah. You can create cooling solutions that are going to be enable you to do those chips. You can probably get away with those in servers. But what you're going to have to do is you're going to be employing liquid cooling. You are going to be doing a lot of investment in trying to make this cooling as flat and as close to the chip die as possible. So you're going to end up with something that is not going to be viable as an end user product.
Actually, the kilowatt already pushes very much through, would stretch the limits of what water cooling, regular water cooling.
Yes, but I would say that you could do this in industrial application. Yeah. But when it comes to end user, you are going to always be dealing with people who only have air cooling. Water cooling can be done, but it usually isn't done because it's too expensive and people don't like water.
It's messy.
It's messy
to clean it.
This has been solved, but the thing is that people don't like it.
No, it's been solved for pre-built systems, but if you want to do your own, you're still going to face the same problems.
Okay, but the other thing is that people just don't want to do this.
Yeah.
And so you're ending up with a power envelope that is probably under 400 watts, if that much. Mm-hmm. We are probably dealing with something like 300 watts or so. NVIDIA, unfortunately, tried to do the 600-watt chips. This didn't end well, partly because they had problems with cooling, but the other set of problems was not only the cooling, but also the power. The power, because you need to, if you're using 12 volts, electrical engineering just says that you have to have 50 amperes of power going through whatever wires you have. So suddenly you are hit not with your wishes, but you are hit with the actual world and actual world physics stopping you from doing some things.
Yeah, I agree.
You cannot create transistors that are smaller than, 4 atoms. You cannot create a big die because this is going to be running into the problem with the speed of light, because it takes a certain amount of time. Speed of light is quick, but it's not quick enough
Yeah.
We are talking about something like 10 clock times, or it takes 10 clock times to go from one side to the other when it comes to die. If you are doing every multiplication with the biggest die possible, so you're going to have problem with the speed of light. You are going to have the problem with signal propagation. You are going to have the problem with signals cross fading to each other. You are going to have problems.
You mean cross-talking?
Cross-talking, sorry.
Yeah, okay.
Cross-fading, cross-talking. I was just looking at the faders. So cross-talking to each other. You are going to have a problem with the power dissipation. So you will come to a point where you suddenly cannot do anything other than either make the chip smaller or shrink something. And the first thing that you're going to shrink is going to be usable memory, or the size of the registers of the chip, or the number of the registers.
Actually, something that you touched upon, and we can kind of close this part of the conversation about architecture in general with that, or maybe if you have something to add. One super important point, which you kind of silently pre-made, I just want to hit that home for you. It is incredibly difficult to explain to people the difference between a distance of chip within the chip. So let's say L1 cache, L2 cache, L3 cache, whatever amount of cache they have, towards the circuits that are inside, which in which case we are talking millimeters perhaps, to tracing that same idea down the path of memory controller to the RAM, which is a much bigger distance. Although this is millimeters or something, or nanometers, micrometers, doesn't really matter, this is centimeters. And the difference in that, when you calculate latency, is incredible. Hence the reason why next generation of CPUs from Intel and AMD are going to follow the same design pattern that Apple has with M1, 2, and 3, which is built-in memory. That's the reason why this is happening. One of the major reasons why.
I don't like to invoke maths at any point in any discussion, but I just want to point one thing. When it comes to speed of light, the time it takes to go through an 8 or 10 millimeters of 10 centimeters of length is something like 2 times 10 to the power of minus 10, roughly. Today, when you're dealing with gigahertz, you are dealing with 2 to the power of 10 to the 10 to the power of minus 9. So basically, they are roughly in the same order of magnitude range, and this makes you think how many cycles does it take to across different lengths in the chip.
1 to 100 is an easily achievable number when comparing L1 cache to RAM.
Yes, and this is one of those problems. And
it's my memory hierarchy problem.
Yeah, but what I want people to understand is not the numbers. The numbers are not relevant, but I want people to understand that things that we consider impossibly small or impossibly fast suddenly become a thing. So a transistor can be as big as, I don't know, 4 atoms. That's it. You cannot reduce the size anymore. If you if you can, in some way or form, lose 1 atom, you're going to reduce the size by 25%. But still, this is going to be a big problem because you need to do
mother physics and mother nature will not easily.
You need to do quantum mechanics on the atom level in order to be able to do something with the current. And I don't want to start about how much current can you put through 4 atoms of material.
That would not be a good discussion.
So this is just one of those things when you need to take into consideration that some things are just simply not possible.
Hence the reason why the path of development over the course of the past, let's say 50 years, since Intel started developing products, was marred with actually many more successes than failures. But still, there were quite a few. And there were big ones, and there were actually big ones recently as well.
But sometimes the solution is just to not try in this particular direction, do something else.
Yeah.
And this is one of those things when I want to start with. I just want to start with the Intel's side of the story.
They were originally a corporation who produced memory.
Yes,
this was there for SRAM.
Yes, I know.
Incredibly important.
The thing is that what they did first is that they got founded. I'm just now reading from the Wikipedia of all the places, but
68?
68, yes.
August 68, I think.
No, July, but it doesn't matter. 68. After Noyce went through first Shockley, then to Fairchild, then he joined Mr. Moore, Gordon Moore.
Not Roger Moore. Yeah.
Gordon Moore, the guy who did the Moore's Law, which I think is one of the most miscited, misguided, and misused laws that ever existed.
We'll have a chat about that, but in some other episodes.
Yes, so, and they got joined by an investor because you need money. And basically what they did is they were trying to develop SRAM and DRAM chips firstly, because what they had is they had an idea on how to use the technology that they were developing previously. And this technology was heavily weighted towards producing transistors. And once you have a small transistor, a memory is the next big
Thing to tackle.
easy thing to do.
Easy, yeah, right.
Yes, because you don't need anything else other than the capacitor and transistor to create a memory.
Okay.
And you don't need to do logical gates. You don't need to do too much complicated electronics. You can just stack transistors.
There's still a fundamental difference between doing a transistors for the purpose of computing versus memory. The few, because these two types of circuits are digital versus analog. That's completely different
Yes, but
discussion.
the thing is once you have the transistors that they had back way then, compared to the transistors that we have today, they're as big as a house, probably.
Yeah.
So we can just say, okay, this was the period when people were able to do something, and the thing that they did is that they suddenly they realized that people around them were trying to create not only memory, but something that's going to be able to do some computing. And this was when the 4004 came to be.
Preceding, actually, it was after the first SRAM chip which it did,
Yes.
which was 3101.
Yes, but it took them something like 2.5 or 3 years to create this first processor.
But it took them only months to create SRAM. That's
Yes,
something
yes.
that's oftentimes missed.
And
Just a
but
couple of months.
The thing is that what I want to point out is that 4004 and then 8008 after it came. I'm just going to check, but I think they came something like
April 1969, 4004. And 808 was April 72.
November 15th, 1971 was the launch date for 4004.
Oh, right. I missed.
then the Intel 8
the order for the CPU for the calculators, whatever it was, came in.
Yes,
yeah, you're correct.
and the
It
thing
took them
was
3
the
years.
thing that I wanted to point out is that 4004 was November 71 and 8001 was April the next year. So 6 months after this. And
They were working in parallel on those designs, actually.
And
but
the thing that was initially confusing to me, and
Okay.
this is the reason why I like that you mentioned Bitness, is that when they did the 4004, they did the 4-bit chip that was capable of doing 12 bits multiplexed address memory. And then when they did 8008, they did an 8-bit chip capable of talking to 14 bits of memory, which kind of doesn't make sense unless you understand how many problems did they have to create a die that was able to support 8-bit calculations. And I think that the number of transistors, because it was 3,500, the number of transistors just tells you that they had a huge problem when trying to fit everything that they had onto the die.
this was 50% more transistors than 4004,
Okay, but
which is a lot.
Yes, and the other thing is that they were doing it in parallel, and people don't seem to understand that you could probably consider that 4004 was basically not a prototype, but just a demo sample of what can be done. It wasn't I don't consider it a real processor.
Okay.
It was the first one. It was expensive and so on and so on. But I think that since it came out in as the first one. It was discontinued in 81, so it was on the market for 10 years. 8008 was discontinued, so it came to the market 6 months later, but discontinued 2 years later in 83. 80, I'm going to just go with discontinuation date because this is just one of those things that is interesting. 8080, the next one, came out in the 74, and it lasted until 1990, so 34 years. 8085, the next one,
Yeah, precursor to 8086.
which was released in 76, lasted until 2000. And then the 8086 lasted until 1998. So it's strange to see different CPUs coming out one after the other, having completely different discontinuation dates. And it points out to some of them being more important than others in some particular usage cases.
I mean, 4004 was a chip that was originally developed for a calculator, I think,
Yes.
a desktop calculator or something. So that's a completely different use case to a Apollo guidance computer or some kind of a server or something like that. It's not even something that you can compare. So definitely different use cases, and hence and popularity meant that the different products lasted longer, let's say, were produced for a longer period of time.
So let's now talk a little bit in depth about 4004.
Okay.
Because it was the first one. It was the first commercially available CPU. Whatever people say, it actually was. The
Programmable,
thing was,
very important.
The thing that was important, that was also on a single chip. Because you could argue that there were microprocessors or CPUs available before that, but they were made up of different chips that then created a circuit that was behaving like a CPU. But this was the first one on a single chip. The idea of energy efficiency was what was important back by then, because the discrete circuits were wasting a lot more heat than the integrated CPU. But the thing is that people also tend to forget is that the speed was abysmally slow. 740 kilohertz.
Yeah.
So 0.7 megahertz, and this is from today's perspective, it's abysmally slow. It's something you wouldn't find in anything, including watches or any conceivable device around us. Because I haven't seen oscillator that is below megahertz in a long time. So it was slow, and the thing was also that it was able to address only 64 bytes of memory.
There's one more very important bit of trivia for that CPU, because as far as the modern day idea of the CPUs go, as you said, it was the first programmable CPU, which was basically one chip. It had something like 50 or so, maybe a little bit less instructions.
Yes.
This is what is going to be a very important topic of discussion as we go on with many different generations of Intel CPUs, which are going to come in future episodes.
I think that is going to be the first thing that we are going to do in the next episode, because right now the number of instructions is not
in thousands.
And even if multiple thousands, this is one of those problems.
Yeah, 4,000 something was a couple of years ago. If you add additional SIMD instructions, it's just craziness.
But what is amazing for me is because when I was preparing for this, I was asking ChatGPT to give me a breakdown of what was important for this chip and what wasn't. And what
I took a different approach.
No, but the thing is, I also took a different approach. But I wanted to see what the AI or the large language model, and this is the name I'm going to use from now on.
Thank you.
Is what is stored in the language model as something that prevails. And the most interesting thing is that the cone on the negative side of the 4004, from ChatGPT's perspective, is that it was lacking support for multitasking.
It was lacking support for multitasking. Holy moly, that's not going to be a topic for 30 years.
No, but the thing is that way back then, people were trying to create support for any sort of task. So any tasking was a
I mean,
problem.
time-sharing mechanisms were the future.
Yes, and as I said, any tasking was a problem.
Yeah, any task was a actually, to your point, basically we talked about operating systems supporting multitasking in previous 2 episodes when we were talking about OS2, which, sorry to say, end of the 80s and up to mid-90s.
And this is one of those things when you are dealing with older computers, older architectures, and so on. It's important to understand the context.
Oh, yes.
The context is something that makes sense when you are trying to understand why people did the choices they did. Why were they not simply addressing, I don't know, 16-bit of memory or 32 bits of memory? For example, you could address more. You could be made to address more. But it made no sense from 2 particular perspectives. One was you needed much more of transistor space on the die, and the other thing is that you couldn't buy much more memory. Memory was extremely expensive.
No, it was almost non-existent.
And so buying a megabyte of memory was just a thing that you didn't do. So addressing 64 bytes of memory, okay, it was small, but at the same time, it made sense because 64 bytes of memory actually had some monetary value back then. Today, 64 bits of memory is rounding error.
No, bits, bytes, or megabytes, we don't care.
Yes. So this was the 71.
Okay.
Now let's go to 8008.
No. There was actually a chip before that.
Which one?
4040.
4040, okay, yes.
This is 72.
You do the one.
Yeah, they added 14 instructions to existing 46 or 48, if I remember correctly. They added a larger stack, bigger program space, and interrupts.
Okay.
Super important. So basically 4040 is treated as one of the first CPUs with the capability to do interrupts. Again, topic that we're going to cover in some of the future episodes.
But the thing is, why did they do that?
Pioneer.
Okay.
For the spacecrafts, if I remember correctly. Pioneer 10, Pioneer 11. If the joke goes that if we could ever find them again, somewhere floating in the space, then 404 and 4040 are going to be representatives of the Earth technology at the time, which is kind of funny. That's all the trivia that I want to do about 4040 because it was not, by any stretch of the imagination, as important as the CPUs that are coming.
Yes, but I also need to point one more thing, and that I actually forgot. The multiplexing part.
Okay.
Because what they had to do at the same time is, as the development and as the engineering is prone to do, they had to, at the same time, create a new processor, but the constraints were much and very, very real. And they had a problem because they couldn't get, didn't have enough pins on the processor, so they had to multiplex the talking to the address space, so talking to the memory, because they were left with something like 4 pins. So they had to actually use those 4 pins to denote which address they are talking to. And this is just one of the small things that I'm always trying to explain to the students and to everybody else who wants to listen to me about the processors. And this is that what you can put on the paper as the processor design and what you can actually create are 2 completely different worlds.
Oh, yes.
Because you can say, I need a 64-bit processor with 64-bit memory space, with
data bus,
with, I don't know, 128 registers and so on and so on and so on and so on. But in reality, you're going to be limited by power, you're going to be limited by the number of pins, you're going to be limited by motherboards, because
physical space becomes a problem.
Suddenly you are going to be limited because you need to talk to other people. You cannot just create a processor. You need to create the entire ecosystem so that processor can actually run. So you need to consider, way back then they didn't need to do this, but now you need to consider which type of memory you're going to use. Is the memory quick enough? Is the memory able to connect to your PC or your CPU at all? So there are a lot of different things that you need to think other than how is the CPU going to look like inside.
Actually, to your point, which is going to become a very important topic of discussion in episodes about Intel CPUs that are coming later in the series. You mentioned that's why I started with the bitness, because it's fundamentally the most important part of the story to understand from a general user perspective. When talking about bitness, there are multiple different types of registers, data paths that use way larger bit sizes. For example, let me give you an example: AVX instructions. So multimedia instructions that you can use to accelerate stuff like encryption, data compression, and whatnot. I think, if I remember correctly, the first generation was 256-bit and the second one was 512.
Yes.
This is enormously big. Hence the reason these registers are a part of the CPU, and they're there with the reason. Exactly the reason why Intel and AMD are nowadays introducing AI registers into the CPUs, because they want to accelerate certain different types of workloads. And that's a smart thing to do if you have the workloads that are common. But the bitness itself is so varying depending on the CPU's generations, use cases, and of course the design of the CPU, MMX instructions, AVX, virtualization registers, whatnot. They can vary in size. It's completely different story too, whether or not you have a 64 or 42-bit CPU or 16 or whatever. Those are completely different discussions.
Yes, but on the other hand, this is the reason why we are now talking about the 4-bit CPUs with extremely small sizes, and we are not talking about, for example, GPUs, because the GPUs are a whole different universe, not only world.
Yes.
And they have their own laws, the ways that they are being designed, the ways they're being used, and so on and so on. And we're going to talk about those later.
Yeah.
But now it doesn't make sense to do this.
Yeah.
Let's just go back. Let's just continue, and let's just go with the thing that 8008 or 8 is 8. Was the processor that was introducing the 8 bits as a normal regular size of register. And I think that they decided that for the time being, this is enough. So they're going to be working...
1972 for context.
Yes, they're going to be then switching over to trying to make use of this 8 bits of information, and then try to expand on the amount of memory that they can talk to, the speed, because it was running at 800 kilohertz, which is also slow.
Yet still much faster than previous.
Yes, but it was much faster than previous, but it was able to address 16 kilobytes of RAM, which was good, but not good enough. And we had to wait 2 years before 8080 was introduced. And I think that 8080 is the next big step after 4004.
Oh, heck yes.
Because 4004 made sense because it was the first one. 8080 was the first real one. The first processor that was intended to be a processor for a general purpose computer.
Yeah, you could argue that kind of jump-started the whole x86 discussion in a sense.
The other thing was that it was the first one over a megahertz. Suddenly it was 2. It was also the one that was able to run CPM.
Yeah.
And this means that suddenly you had something that was able to run an operating system that had some traction already.
Yep.
So you were able to go and use something that was available on the market, and you can also cross-compile things that were available on the market. So it made much more sense from the end user perspective because it enabled end users to use something.
There are actually, I read some articles months and months ago when I was reading something related to my PhD studies. And a lot of people now argue that Z80 and 6502 were heavily influenced by 8080. Heavily influenced by that in terms of the design and some of the general principles, which kind of makes sense because at the end of the day, those were the mid 70s. That's where computing basically was born as a general idea Like not for specific use cases. It was becoming much more available, and with the coming of the Spectrums, the Ataris, the Amstrads, all of the other things that we already kind of talked about, it was like a dawn of a completely different time that was looming very, very close on the horizon.
Okay, this is one thing, and the other thing is that 8080 came out a year before 602. And I think that it influenced the 602 in some ways, but also I think that the influence was...
It also anti-influenced 6502
Yes,
in ways.
this is one of those things. It also pointed to the 602 development team which parts of the processor were misdesigned. And one of those things was that 602 was probably the first one that supported a single voltage, because it didn't require different voltages for different parts of the processor. And this made creating circuits with the 602 much easier.
Yeah, and cheaper.
Also, 602 was drawing less power, so it was easier to cool down. Or from today's perspective, being able to cool anything down passively is an amazing thing. So being easier to cool down means that 602 was able to pull it off even without having any thermal solution on it. And what Intel needed to do, they needed some sort of cooling. By cooling, I mean something that was connected directly to the CPU die and just dissipating energy. But
actually, your point with having multiple voltages is incredibly important.
Yes, because this was 8085, which came out 1 year after 602, so 2 years after 8080, did the same thing.
Obviously, Intel understood that that's the way to go.
But I think this is one of those things where the market was such that first, development wasn't that expensive.
Okay.
The number of units that you had to ship wasn't that big. So it was much easier to just switch to new technology and to make things up as they went along.
I mean, one of the fundamental complexities of the PC market, still present today, is the fact that various parts of the CPU as a device use different voltages. It's a widespread problem, which we don't think about today. 5 volts, 12 volts, 3.3 volts, roughly 1 volt for the CPU with a lot of amperes.
Yes, it took them amazing amount of time before they were able to actually push out -5 and -12 volts.
Exactly.
And this was a huge effort to try to just go with the positive volt values and not have a spread of basically 24 volts across different rails.
This is actually something that's slowly but surely changing again. I saw some specification, I think it was for some kind of a new ATX standard that's going to kind of standardize on maybe a little bit less different voltage levels or something. I have to read about this, but I heard a story about it, which I find to be completely irrational that this wasn't done 20 years ago.
But the thing is that also...
I mean, there's an architectural reason why. Mechanical devices, hard disks, optical disks, whatnot, they needed more power.
Yes, but I think that they were one of the first ones that realized that this is creating a problem, and they switched over to using just 5 volts.
People who did 6502 were amazing bunch of people. They really understood their stuff.
And I still think that 602 is way better than anything else before Z80.
There's a reason for that, why that CPU is so popular still.
And what we are talking about today is just a string of or a stream of CPUs that Intel created. They were incrementally better one after the other, but on the other hand, 602 is still being produced. The current designation is 6C02, and it is running at 24, I think, megahertz or 32. I'm not sure. I know that I checked, and the number of produced units is something like
billions, probably.
130 billion units up to date, and I think they estimated that they are producing 100 million each year.
Yeah, I'm not surprised at all.
And the thing is, why the estimation? Because nobody actually knows.
Yeah, it's possible.
It's possible, but since the patents expired,
Everybody
And
can make one.
everybody can make one, and also everybody includes one in their own solutions. So, for example, some
Controllers.
microcontrollers like ST something are using 6202 as a part of the microprocessor. So they share part of the die is just 6202, and then the rest is the rest of the processor.
One other thing that I noticed, I actually read bits and pieces of the Intel archive in the past couple of days, and I found their articles to be quite honest, actually, to a fault. They say that 8080 was a paradigm shift marking the transition from large mainframe computers to the advent of personal computing. Insanely important thing that happened with 8080. So because the echoes of the 8080 and the consequent, let's say, competitors like 6502 and Z80 and a couple of other CPUs, their influence on what happened afterwards is seminal. It's just impossible to overestimate how all of those CPUs were important for the things that we have today on the market, actually, all the way till today. And 8080 was already capable of, if I remember correctly, it was capable of addressing 64 kilobytes of memory, which was, it was quite a shift from 16 kilobytes of 8008.
Yes, but the thing is that the things stopped being so aggressively all over the place with the 8085. Because I think that this was the first processor where Intel got their feet completely wet, and they now understand how to create a processor. So they were able to do some sort of a thing that's going to be a revolutionary way forward, without just introducing another similar processor to the ones before it.
You know what's one of the biggest differences between 8008 and 8080?
80, okay, no?
The amount of pins that those CPUs had.
Okay.
To your point, which you made earlier. If I remember correctly, 8008 was 14 pins or something like that. This one was 40.
Yes, the thing is that, to be completely honest, Intel always had a problem with the number of pins. And this is one of those design things that they are trying to solve, but for some reason or the other are not able to. I'm just pointing to much later in the Intel's timeline. Almost all the different new architectures were completely incompatible with the number of pins of the previous architecture. So
AMD did the same.
Yes, but suddenly
a little bit more rarely, but still.
Yes, but now they're sticking to their pinouts for the last couple of generations, and this makes upgrading your computer much easier. And this is one of those things where we are getting a more mature architecture, because the changes in architecture don't require you to change everything in your computer. You can do a normal upgrade, and this makes upgrades cheaper.
Yeah. And
easier.
Much more attractive to users as well.
Yes, and this is the thing.
I mean, buying a new motherboard every time you buy a new CPU is not fun.
On the other hand, when it comes to quality motherboards, it makes sense, because either way you're going to have a crappy motherboard.
Yeah, I never bought cheap motherboards. That's my problem.
The thing with the cheaper motherboards is that you can buy multiple of those.
Yep.
So you buy one, you wait 6 months, you buy another one, and then you wait 6 months, and so on.
No, thank you.
So you always have the latest technology.
Yeah, incremental upgrades by Yasmin. A new show that we need to do.
Yes. So, anyways, 8085 was an incremental update to 8080,
leading to something much more important,
and then leading to something that was 8086.
Yep.
And now let me go back to something that I was just going through, and what was interesting to me is that...
By the way, that's probably the first CPU that was made after you were born.
Yes.
76.
I didn't want to mention this because I am that old. Why not? What is the release date of 8080? Oh, okay.
It was in 1976. I don't remember the launch date.
8080 was in 74. But
sorry, I was talking about 86.
And 86, yes. So 8086, The thing was that one of the biggest things that 8086 had was the number of transistors.
Okay.
Because they jumped from 6,500
Thousand.
transistors to 29,000 transistors.
Basically, it's a foreshadowing of what's about to happen in the future.
And it took them only 2 years to make the jump. And this is one of those exponential things. And the other thing was the speed didn't increase that much at first, but then they jumped. In the end, the speed of 8086 was 10 megahertz, and the 8085 was up to 3 megahertz. So the speed was incremental, but the number of transistors wasn't. It was exponential.
Okay. It's also a 16-bit CPU, very important.
Yes.
86. Up to 1 megabytes of addressable memory or something like that, if I remember correctly. So it had 16-bit ALU, 16-bit registers, 16-bit internal data bus, external data bus. It was way faster than anything that preceded it. Way, way, way faster.
Yes. And I think it was one of the first extremely competitive CPUs that Intel had.
Correct.
Because
Followed by an even more competitive one.
Because when you compared it to what was on the market back then, 6002 wasn't even close.
Z80
the same. Motorola had some processors that were comparable to what Intel had, but this was the first one that actually was making a niche for itself in a completely new market.
Yep, agreed. Okay. And next in line, unless you have anything to add to 8086, is 8088.
8088, okay.
Super important CPU. And I'm not saying that for selfish reasons, because as I mentioned in one of the previous episodes when we were talking about our computers, my first PC was 8088 based Commodore PC-10-3. It's not about that. It is 1979 revision of 8086 CPU. Very similar to it. But a little bit on the, let's say, low-end side, because they shrunk some things from 16-bit to 8 bits, blah, blah, blah. The clock frequency, as you said, for 8086 was 5 to 10 megahertz, if I remember correctly. So I remember this vividly because I had a computer that was based on 8088 for years and years. That one actually had basically programmable speeds, 3 different programmable speeds, if we are completely honest about that one. 477 megahertz, which you can equate to 5, roughly. 7.16, if I remember correctly, and 9.54, which you can again equate to 10. This was changeable via keyboard. Control Alt A, S, and D were the keys that were from left to right, bringing you to the faster speed. I remember that vividly because I did that a million times just for fun, because almost always you kept your computer at the maximum frequency. The only notable situation in which you didn't was, for example, playing Tetris. Or something like that, because at lower speeds it was easier to play because the game was slower. But as you got more proficient, you bumped the speed up from Control Alt A to C to D, and at the end you played at the maximum speed, and you could play that for hours, and everything was cool. Basically, it's a metaphor for what people use for a variety of different games. Tetris just being a metaphor that I use because I'm very familiar with it. We talked about the architecture of that specific computer in one of the previous episodes. I said it was heavily expandable. I had 2 floppies. I had a built-in hard disk that was 20 megabytes, which for the time was like having a house with a pool in terms of the amount of space that you had. It had every single conceivable connector on the backside that you could possibly think of for the generation, serial ports, parallel ports, outputs for whatever, built-in speakers. So it was a really good computer. And I vividly remember that, but I also vividly remember the technology, which was, that computer was 50 kilos heavy. It was super heavy, and the monitor and the keyboard, and it had some other stuff. It had some issues with cooling and some other things. Generally speaking, it worked really well. But the thing about 8088, 8088, so 8088, before I kind of like mess it up. So architecture similar to 8086, 8-bit external data bus versus 16. So that was shrunk
Yes,
from
and
the
this was the
86.
main reason why they did it.
Okay.
Because they wanted to enable, no, they wanted to enable people to use memory that was only, that had only the 8-bit data bus.
Yeah.
And this enabled them to use cheaper memory.
Yeah.
And at the same time, since the internally it was still a 16-bit processor, it was able to process the data quickly. So what they ended up with was a quick processor that was able to be compatible with the older types of memory. So it was cheaper to use.
Yeah, it was cheaper to buy, cheaper to use, and everything
Cheaper
else.
to, specifically cheaper to use because everybody had motherboards and everything else also well designed for the 8 bits. So including a processor that was behaving like an 8-bit processor and being able to process 16 bits made sense.
It had I think 640 kilobytes of memory, if I remember correctly.
Okay.
I think I got that one right. But there are other things why 8080 is so super important. So it kind of followed after 8087, which was the 7 number on Intel was always related to something like co-processing in those days, whatnot. 8088 had the capability to do floating point as well as the integers, which was quite a big addition to the capabilities of the CPU. Because it supported the 8087 types of instructions and the capabilities. And, it in terms of the pinout, it was also quite configurable. It had, I think, 40 and 44 pin pinout for 8088 CPU. There were 2 different distinctive variants for that, depending on some of the built-in features and whatnot. And if I remember correctly, that CPU also had the capability to address up to a megabyte of memory, which was, again, if you had a megabyte of memory in those computers, you were, call me Prince of Bel-Air.
Okay, and the other thing is that also that needs to be mentioned is that this was one of the first chips that were outsourced and that were basically they gave permission to other manufacturers to license the IP or the property of the processor itself to create their own clones.
We are going to have a separate episode about
Yes,
the
about the Clone Wars and so on.
Super important.
This was one of those things that made sense back in the day because what Intel realized is that they don't have enough manufacturing capabilities. And instead of doing the IBM thing and just stopping the production, they decided they're going to license it to NETs, then to Commodore, then to Oki, and to different. And this is the reason why this was important also is because it took them 2 years to go from $124 to $14 per chip in price, which made the chip much more interesting to everybody who's trying to create something. And also, taking into context everything else, this was an important thing because suddenly you could produce any system that you wanted with the chip that was available, and it was widely available. And IBM forgot to understand this, or it was unable to understand this. And what they created for themselves was that all the chips that IBM created were pretty much relegated to just doing what IBM wanted them to do. They weren't people.
Corporate mentality.
Yes, people didn't have the opportunity to be creative with the chip.
I vividly remember those years when we got the Commodore PC-10 free, as I was in primary school, near something like grade 7, something like that, grade 7 or 8. Our primary schools are 8 years long, just for context, for our listeners from abroad. And we, my brother and I, had a lot of discussions about which computer we were going to buy. At that point in time, we were still using the Amstrad, so CPC 464. One of probably my favorite computer of all time. Sorry about your Z80s and other people's C64s. There's a reason why I'm saying that. It was just an excellent combination of fragility, tranquility, usability, and incredible amount of frustration trying to make the cassette player work properly and whatnot. We can get into that in some other episodes. But we had such an enormous amount of discussions, my brother and I, about which computer to buy because the Clone Wars were starting. They were already on the market when because we didn't buy it out like when it first came out. We waited a little bit. And we basically what we went through, which is a reoccurring theme from personal perspective. I know you had something similar because we talked about it. We started sifting through every single conceivable book, article, magazine, whatever was available. Internet was not a thing then. There's, 10 plus years before internet became widely popular. And we were trying to make an informed decision about which way to go, because we could have easily gone with Atari at that time, easily. The strongest models were super popular. Actually, in our ex-country, a lot of Ataris were sold and being. I know a whole bunch of people in my neighborhood who had them. Actually, they outnumbered everything else by a factor of 10 at least. It's incredible to say that. But we settled on that specific computer and then on PC as a platform. And then we bought a dot matrix printer and all of the other stuff that went with it. This was my introduction to PC. You went through something similar, but your first PC wasn't XT, I think.
Yes. And then didn't directly buy it. So this is one of those things where the price didn't matter as much. To be completely honest, in the late 80s, start of the 90s, going with the PC as a way was something that people usually didn't do.
Yes.
Because PC was...
Amigas were much more popular in my neighborhood than PCs.
It's not the popularity. The thing was that PC was more expensive.
Yes.
Less capable.
Yes.
Way less capable when it came to audio and video.
Yes.
It required its own separate peripherals, so the monitors were required and so on and so on. And this was one of those things where people actually didn't buy into the ecosystem because they didn't have enough money.
Exactly correct.
You had your TV. You didn't want a separate monitor.
Yeah.
Now, buying a monitor is just a question of which one do you buy.
Yeah.
Back way then, you couldn't get a monitor, and if you got it, it was extremely expensive.
Yeah. I remember more than a few of my friends having Amigas. Amigas were a thing back then, and Ataris as well, which were already very popular in musical studios. Because they had built-in MIDI, so they could control the synthesizers and whatnot. The synth revolution already happened. So there was a reason why basically making a decision towards going to PC was kind of like a risky one in a sense. And I kept that computer all the way till I signed in for college. All the way through my high school, I had that one. I didn't buy anything else. And then skipped 4 or 5 generations of computers to 486, Clone Wars 486, DX4 120 or something like that by IBM. This is something that we're going to discuss in future episodes as we go through the Intel history.
I'm just going to go through, since we are going to be slowly wrapping up this thing, I'm just going to go with one more information. And this is I was just reading up on the reason why 8088 or 8086, why they switched from 5 megahertz to 4.77.
Okay. Crystals or?
No, the reason was NTSC.
Because
that
makes sense.
IBM but basically tried to create a computer that is going to cover everything. Mm-hmm. So they were prepared to not only include regular monitors as something that they're going to be dealing with, but also the TVs, if the need arises. And the other thing was that they were, if you remember, in the BIOS of the PC, they were able to support tape drives. Mm-hmm. They didn't use them because the tape drives basically became obsolete as soon as the IBM PC went to the market. Mm-hmm. But they were capable of supporting them directly. They were capable of supporting NTSC directly. So this was one
picture format that was very popular outside of Europe. We are PAL system.
We are PAL here, Japan, and NTSC was Japan, US,
and other countries. Yeah.
And this was just one of those things where I think...
Secam and Mesicam were popular in France. And so I remember those days. Buying a VCR was complex.
Yes. I think that the last time they tried to pull it off was with DVDs and zones. Yes. So anyways, what was interesting is that IBM didn't make... but persuaded Intel to create a CPU that's going to be much easier for them to use in the IBM PC. And this is one of those things where this thing started. Intel was creating something that IBM could use for the next generation of the PC. So Intel decided to create something cheaper, less powerful, but more compatible to what IBM wanted.
Yeah, that was a sound business decision by Intel back then, because in a matter of couple of years, PCs were everywhere.
Yes, and the other thing is that what I simply don't understand, and let that be a preface to the Clone Wars. How did IBM think that they're going to be using a CPU that is at the same time, I would say, I won't say designed, but converted and specialized in a way that IBM required, and that Intel at the same time licensed to all the different manufacturers outside of the IBM ecosystem. What was the IBM's idea behind
The premise
it?
behind that is just unclear.
Because if you have...
Actually, it's clear. We are IBM, you are nobodies.
Yes, and then what they were expecting Nets to do what? Wait for the IBM to come with the same processor that they are licensed to do.
Can I tell you a very short, let's say, IT joke that only you and I and a couple of people listening us are going to understand? In the whole of my life, I only had one IBM, and it was a ThinkPad.
Me too. And the reason was that in one particular... I had one IBM desktop, and I don't remember which version was it, and I got it probably 12 years after it was made, as one of the old computers that I always have from people who say, okay, you're collecting old computers, there you go. And it was one of those units that were strange computers that didn't make any sense at any point in time. But
I did get a desktop computer with IBM CPU inside, but it wasn't IBM's computer. That's even weirder. Story for another day.
Okay, let's wrap this thing up because we have arrived to 8088, and then we are going to be continuing
with 1, 2, 3, 4.
Yes, but the thing is that almost all the materials that are covering Intel's versions of the processors, when the 8088 is mentioned, they say, okay, after this, all the different chips that were based on it were 80, 186, 286, 386, 486, Pentium, and so on and so on and so on.
686.
And as a side note, almost all the motherboards right now on the market have 486 on the motherboard.
Yeah, a part of the
part of ePro. So this was just one of those things. So thank you for being with us.
Yeah, this is much fun to do.
Yes, and see you next week.
Yeah, see ya.
Bye.